The universe is a symphony of energy, constantly shifting and transforming. Heat and electricity are two fundamental players in this grand orchestra. They are intimately intertwined, their fates forever linked. Thermoelectricity explores this fascinating relationship, revealing how we can convert heat into electricity and vice versa. One of the key movements in this thermoelectric symphony is the Seebeck effect, discovered in 1821 by Thomas Johann Seebeck. This effect demonstrates that a temperature difference across a conductor can generate an electrical voltage. Imagine heating one end of a metal rod. The electrons at the heated end become excited and start to move around more rapidly. This increased movement causes them to diffuse towards the cooler end, creating a voltage difference. The Seebeck effect is the foundation for thermocouples, devices that measure temperature differences. These ingenious instruments are used in a wide range of applications, from monitoring temperatures in ovens and furnaces to controlling engine performance in cars. But the story doesn't end there. The Seebeck effect has a lesser-known but equally intriguing counterpart, the Peltier effect. In 1834, a young French physicist named Jean-Charles Athanase Peltier stumbled upon a curious phenomenon. He observed that passing an electrical current through a junction of two dissimilar conductors could cause heat to be absorbed or released at that junction, depending on the direction of the current. This discovery, now known as the Peltier effect, would have profound implications for the future of thermal management and energy harvesting. The Peltier effect can be thought of as the reverse of the Seebeck effect. Instead of generating electricity from a temperature difference, we are now using electricity to create a temperature difference. This remarkable ability to pump heat with electrons forms the basis for a whole new class of solid-state devices known as thermoelectric coolers, or TECs. To understand how TECs work, we need to delve into the world of semiconductors. These materials, with their unique electrical properties, lie at the heart of modern electronics. In a TEC, two different types of semiconductors are joined together, N-type and P-type. N-type semiconductors have an excess of electrons, those negatively charged particles that carry electricity. P-type semiconductors, on the other hand, have a deficiency of electrons, creating holes that act like positively charged carriers. When an electric current is passed through a TEC, electrons flow from the N-type semiconductor to the P-type semiconductor. As the electrons cross the junction, they absorb heat from their surroundings, effectively cooling that side of the device. This absorbed heat is then transported across the junction and released on the other side, where the electrons recombine with holes. Section 4. The Peltier effect in action, from cooling to power generation. The ability to create a temperature difference simply by passing an electrical current has led to a wide range of applications for the Peltier effect. One of the most common uses is in thermoelectric cooling systems. TECs are found in portable refrigerators, wine coolers, and even high-performance computer processors. They offer several advantages over traditional vapor compression refrigeration systems. They are smaller, quieter, and more environmentally friendly, as they do not require refrigerants. But the Peltier effect is not just about keeping things cool. It can also be used to generate electricity from waste heat. Imagine capturing the heat from a car's exhaust or an industrial process and converting it into usable energy. This is the promise of thermoelectric generators, or TEGs, devices that exploit the Seebeck effect to turn a temperature difference into an electrical voltage. Section 5. The efficiency challenge, a balancing act. While the Peltier effect holds immense potential, there is a significant hurdle to overcome: efficiency. The efficiency of a thermoelectric device is determined by a figure of merit, denoted by the letter ZT. A higher ZT value translates to a more efficient device. Unfortunately, current thermoelectric materials have relatively low ZT values, limiting their widespread adoption. The challenge lies in finding materials that are good electrical conductors, but poor thermal conductors. This unique combination of properties is essential for maximizing the temperature difference across the device, and consequently, its efficiency. Section 6. Pushing the boundaries: advancements in thermoelectric materials. Researchers around the world are actively searching for new materials and fabrication techniques to enhance the efficiency of thermoelectric devices. One promising avenue is nanotechnology. By engineering materials at the nanoscale, scientists can manipulate their thermal and electrical properties with unprecedented precision. Another area of exploration is the development of new thermoelectric materials with complex crystal structures. These materials exhibit unique electron and phonon scattering mechanisms that can lead to significant improvements in ZT values. Section 7. A future powered by heat, the promise of thermoelectrics. Despite the challenges, the future of thermoelectric technology is bright. As research progresses and efficiency improves, we can expect to see a surge in applications for the Peltier effect. Imagine a world where waste heat is no longer wasted but harnessed to power our homes, cars, and industries. Thermoelectric generators could be integrated into everything from car exhaust systems to power plant chimneys, capturing waste heat and converting it into usable electricity. Thermoelectric devices could also revolutionize portable electronics. Imagine smartphones and laptops that charge themselves using the heat from your body or the surrounding environment. The Peltier effect, once a scientific curiosity, is poised to play a pivotal role in a future powered by sustainability and efficiency.